So the previous recording has been cut off, so let's just restart for the last bit of the lecture on finite element analysis. Now we look at how to work out, or the mechanism to work out the stiffness matrix for triangular finite elements. Now for rectangular finite elements, the same uh, algorithm or the same mechanics of working out the K matrix is exactly the same. Now the only difference is that we now have a shape matrix that is of a slightly different form, like that. But everything else are exactly the same. The S matrix didn't change. It's still d by dx 0, 0, d by dy, and d by dx, d by dy, and D matrix also doesn't change, where we have E, not a, it's too sensitive, okay? The Surface Pro sometimes is too sensitive. So D is what? D is E minus 1 over mu square 1 mu 0 mu 1 0 0 0 1 minus mu over 2. Now just recap, this is an operator, and this is basically a matrix of some constant. And this here is a matrix that contains some info on the coordinate x and y. Okay, that's the key things. 3 key things you need to remember for this 3 key matrix in the whole procedure, so you'll be able to understand what's going on. So the first thing again is to work out the B matrix, which is basically x dot n. Now the order here is important because you are literally operating d by dx and d by dy on some big matrix here, where each element here has some sort of x and y in there. So it's a function of x and y in each of these matrix elements for n. Alright, that's why you can actually do the differentiation and matrix multiplication term by term to work out the B value for a rectangular finite elements. And if you work that out, B, what does B look like? Now we don't actually need to do all the math ourselves again, but you just need to understand the principle. So B, this S dot n will be looking like some sort of differentiation times some sort of function that gives you the matrix elements for B. Okay, this is very important to remember how this B work, right? So if you do go through this kind of operation, you can see that sorry about things moving around, but You can see that the B matrix is 1 over AB times y minus B 0 minus y 0 B minus y 0 y 0 0 x minus a 0 a minus x 0 minus x 0 x and x minus a y minus b a minus y minus y minus x b minus y x y. Okay, now you don't need to remember what this B matrix exactly is. Again, this is done by a computer. Again, what you need to understand is B somehow incorporate the geometry information of your finite elements in terms of, for example, the length and the width of your matrix, or the rectangle that you build up. So this A and B in there, and it kind of depends on the position of the point inside these finite elements, right? So this is the B matrix. Now, in the very last slide of lecture notes, right? Slides 82. That's actually the final K matrix that's worked out from doing B transpose times D dot B. Now this is quite a big matrix with lots and lots of elements inside, but the most important thing you got to remember from the shape of this matrix is that the K matrix itself is symmetric. Right? That means if you have a matrix, the bottom half triangle, if you flip through across the diagonal, it will give you the top part of this matrix. Okay, so that's the value of K for this matrix element. Again, why this K is important? Because go back to the very fundamental things that we want to achieve in finite element analysis is what? It's not actually work out this horrendous K matrix. Is basically we want to use this K matrix to understand, okay, if an system or the finite element is subjected to an external load, which is this guy, how this shape or this structure will start to deformation, right? And to be able to work that out, what do we need? We need this K value, right? So the most challenging part is actually to work out this K value in the whole process of finite element analysis, right? How do we work out this K value is by using the principle of virtual work, which we have just demonstrated you how to do it from the previous 4 videos that include working out the shape function and putting the shape function together to get the K matrix, right? Once you get that, to actually solve this matrix equation is quite trivial. This is basically a standard linear algebra problem where we basically can solve A, right? In the most simplest form is the K inverse times F external. that will allow us to work out the deformation at each individual node. So now that this wrap up the whole course on finite element analysis. Now I know this has lots of algebra inside, but in practice, right, we just want you to understand the fundamental principle behind, being able to be able to know what's going on beside after or behind the scenes of the software that actually do the finite element analysis for us. Okay, so for that, I thank you very much for attending this course. Now, as we have been doing along the way, we'll have regular team meeting online, so you can ask me questions, and hopefully I can have some chance to explain to you a bit better how things work. You will also be able to gain some real understanding of how this thing operate in real life through the lab component that we did on ANSYS. So for that, I conclude the second part of Maths 3006 computational modeling on finite element analysis.